Let's go over the solutions for the exercises for this week. And we'll start with calculating the node voltages in this circuit. Just a quick review. We're going to choose a reference node, which is already this reference node over here, the ground. Then step number 2, identify our independent nodes. Again, that's already done. It's this one and that one. We're going to label constraint voltages, V1 and V2. And then step 4, 5, 6, and 7. This is the one that I'm going to show with more detail. So 1, 2, and 3 done in the circuit. V2 and V1. I'm assigning currents. Again, do not matter the direction that you assign as long as you put the plus and the minus respectively, and then you apply Ohm's law. For example, I1 with this direction is going to be V1 minus V2. If you set up the direction differently, if you set up I1 entering this node over here, is going to be V2 minus V1. All right, so step number 4 and 5 of node analysis, you're going to take your equations, taking equation V1 and V2, simple KCL on that node, so 5 amps entering and equal to I1 and I2 leaving the node. And for V2, I have I1 entering plus 10 amps entering and the 5 leaving and the I3 leaving, and that's what you have here. Then I apply Ohm's law so I can get the current in terms of voltages and resistances. Step number 6, I just start solving these equations, so put everything together, so the V1s together, and rearrange the equation, and then I solve the equation in terms of V1 and V2, and you get 13 volts and 20 volts for the circuit. Let's go over false stat here, and let's simulate the circuit and see what we get. And you can see here that we're getting the right answer. So 20 volts for V2, which is that point over there, 20 volts, and 13.3 for that point. It's pretty cool to simulate, so you can see what currents do in the circuit and make sure that everything is correct. All right, exercise number 2, same thing, node analysis, similar steps. Again, 1, 2, and 3, they're pretty much done. Reference point and the label voltages or the label nodes over there. Assign currents, directions of currents if you don't have, again, arbitrary direction. And step 4 and 5, take the equations for the nodes. So V1, I have I1 and 3 amps entering the node, IX leaving the node. V2, I have IX entering and I2 and I3 leaving. And for V3, I have I3 entering and I1 and 2 times IX leaving. Apply Ohm's law respectively and rewrite your equation. So put the terms that are the same together, and in blue you have the result. Now we could go and try to solve, for example, this V1 in terms of V2 and V3, so putting all these terms over there, then substitute on our second equation, and then you will have everything in terms of V2 and V3, solve everything in terms of V2, and then substitute in your third one, and eventually you start unrolling and getting answers. This is very tedious. There is a faster way to get answers when you have more than 2 equations, 2 unknowns, and what you do is you put your equations into a matrix form. So notice here that these 3, minus 2, and minus 1 are the coefficients of your first equation. And these second one, 4, minus 7, and 1 are the coefficients of your second equation. And these the coefficients of your third equation. And then you put here your variables. So V1, V2, and V3 equals to, and then the result, 12, 0, and 0. Now what you do is if you find the determinant of this matrix over here, which is going to be equal to minus 30, then you can apply Cramer's rule to find the values of your unknowns. For V1, all you need to do is you go to your matrix, and I'm trying to find V1. So I go to the first column because they are all related with V1. So notice here, 3V1, 4V1, 6V1, and I remove those components and I put my output over there. So I get 12, 0, 0, and then the rest stays the same. You calculate the determinant of this matrix. You divide by this one, minus 30, and you get your answer, 4.8 volts. You do exactly the same thing for voltage V2 and voltage V3, but now you're going to substitute on the respective column. So for V2, you put the output on the middle one, and for V3, you put the output on the third one. So let's see this circuit in action. If I put it on false start, here you go. I get exactly the same voltages that you are getting over there. So notice here my V1 is 4.8, sorry. My V2 2.4 and my V3 minus 2.4. Notice here that I'm putting my dependent source over here in terms of the current I of X, and the current I of X is the one that flows through this resistor over here, and you get exactly the same answer. All right, pretty cool. The next slide just reviews really quick Cramer's rule for 2 equations, 2 unknowns, or Cramer's rule for 3 equations, 3 unknowns. Kind of goes over a little bit more into detail, and it tells you how to calculate the respective determinant. And it's pretty easy when you have 2 by 2. You multiply A times D and then minus B times C. And when you have a 3 by 3, you can do actually a similar approach, which what you do is you pick up your A and you put your A over here, and you eliminate the column and the respective row of that A, and you get just a small 2 by 2 matrix, and then you calculate that determinant of that matrix, multiply by A. And then you're going to do the same thing for your B, but you put the minus, and then for your C. And if you sum all these together, you get your determinant. Pretty cool. All right. Problem 7. Problem 7 target is mesh analysis, and this is a quick review of mesh analysis. So first you're going to choose your mesh loop, identify mesh currents. So this exercise at first might seem a little bit tough because they're already giving you some loops over here. When you apply mesh analysis directly from here, you don't care much about these loops. You are going to find your own loops, but this is method number 1 that we are going to use first. It's kind of ignoring what these mesh loops that are here, and we are going to find our own by doing this mesh analysis. But method number 2, we are going to actually use these currents that are here, and we're going to use this concept of super mesh. So let's go over this one over here, the mesh analysis, which we are going to kill the sources first. So a voltage source becomes a current circuit, a current source becomes an open circuit. We're going to identify those non-overlapping areas, finding the mesh loops, and then we're going to find the constraint loops, and then we're going to apply KVL and find those equations, or solve those equations. So let's go over that method number 1. Let's ignore for now these 3 colors that you have over here of currents. Step number 1, let's again find like our loop. This is supposed to be a short circuit over here. This is an open circuit, so it gets out, and I have the loop that you have over here. And now I design the loops. I identify my mesh loops. I have one mesh loop over here and another mesh loop over here, which is this big one. Step number 2, I connect my sources again, and now I'm going to find the constraint loops. So notice that I have a source, a current source over here. So I have a constraint loop over here. It's going to have the direction of your current source, and you can either pick this one or the one inside of this side. It doesn't matter. I'm picking this one, and that current, that constraint current, is equal to 4 amps, equally to that one. All right, so just heads up. Notice that this I is not that high of 2, and this I1 is that I1, and this I3 is that I3. So pretty much kind of is going to give us the solution for now, is going to give us the answer for these 2 currents, and then we need to find this I2 because it's not 4 amps. All right, let's find the equations for loop number 1. Again, KVL around that loop, and you find -8, and then the 2 ohm resistor has the I1 entering, so I1, and the I3 leaving, so I1 minus I3. Then you have the 4 ohm resistor, and the 4 ohm has I1, and then it has I3 and I on opposite directions, and then you have the 8 ohm resistor, and that's it. And this is the equation for your I3. Similar approach, 2 ohms just as I3, 4 ohms as I3 and I entering and I1 leaving, and the 2 ohms I3 minus I1. We rearrange the equation and we find I3 and I1. So far so good. We'll get the right answers. But remember, on step number 2, that I2 is not going to be 4 amps because this is a constrained loop. So how do we solve that? How do we find I2? Well, we go to that node over there and we know that I1, so the current leaving, is equal to the 4 amps plus I2. So I know I1 from the previous step and I get my value of my I2. Problem solved. So let's go over method number 2 that does not use the mesh analysis that we learned. It's going to use this concept of super mesh. And the super mesh, what is this? Super mesh results when two meshes, so notice here that I have I1 and I2, have a current source in common. So notice that they share the same current source. The exercise that we have been doing in class, this current source is not here. Normally it's at the end of the circuit, which only shares one current, one mesh current. So when we have these, what can we do? Well, we can actually apply a method like this one. I'm going to exclude the current source. It's like that open circuit, but I still have my loops. And now the difference here is that this I1, it's only influencing the 2 ohm resistor. It's not going to count for the 4 or for the 8. So when we take our expressions, notice that it might seem similar to the previous one, but I never have I1, let's say here on the 4 ohms or on the 8 ohms, because it's only, the I1 is only counted for this loop over here. I'm treating this as a super mesh, but the concept is pretty much the same. So now after having that, what I'm going to have is I need to apply the same concept over here, which is, we call this a constraint equation, where I1 is still equal to 4 amps plus I2. And now you're going to substitute that into your previous equations and you get two equations with two unknowns. And you get your values of I2 and I3, and then I1, you know, because it's a constraint equation, depends on I2, and problem solved. So now let's go over the superposition. Oh, before that, sorry, let's go and run our circuit. If you go to file stat and you run the circuit, here you go, measuring the currents over there, and these are the values that we get. All right, let's go over the superposition now. Superposition is telling you that if you have a linear circuit, what we can do is, in order to find the total voltage or current that we want to find, we can eliminate each source individually, find that value, then add those values at the end. So the first thing that I'm going to do is I'm going to kill my current source, so it's going to be an open circuit, and identify here two mesh loops. Again, I'm not using mesh analysis, I'm just identifying KVL here, and I write the equations. And I have one equation here, another one over there, and notice that I have only two unknowns, I1 and I0 prime. So I'm calling I0 prime because I'm eliminating the current source. If I solve it, I get minus 60 over 17 amps. I'm missing here the units. And then I put it back and I kill the other source. The voltage source is a short circuit. I identify three mesh loops over here. And on that point A, it's kind of a relationship between I1 and I3 and I0 prime. It connects things together because I have three equations and I need to have three unknowns and not four unknowns. So notice that I have I1, I2, I3 and I0 prime. So by finding a relationship between I0 prime and I3, I can have three equations and three unknowns. I know I1 is 4 amps, I2 is this loop over here, I3 is the one on the bottom. I solve these equations and I get 28 over 9. Putting all together gives me this current. All right, this is the one that is giving slightly different values on file stat, but it's pretty close. And I believe this is because I'm simulating this dependent current with a voltage source, and that might influence a little bit the results over here, but it's pretty close. All right, let's keep going. And now we have the just applying source transformation. What is the voltage that I get across the 8 ohm resistor? All right, so I have my circuit. So notice here that I can pick up this resistor and current source and apply source transformation here, and the same thing with these two. If I do that, that 3 becomes in parallel, and the 12 volts divided by 3 gives you 4 amps, and here is 3 times 4 gives you 12 volts, and the 4 ohms becomes in series with 2. Notice over there that I have another source transformation that I can do. 4 plus 2 gives you 6, and then I put it in parallel. Pay attention here that the current here is going down, so the voltage source needs to be opposite of what you normally are used to. So current now is pulling you down. So it's 12 volts divided by 6, 2 amps. And now from here I have everything in parallel, and notice that V0, it's still the voltage across this 8 ohm. So this current is going up, this current is leaving, so 4 amps minus 2, I can have the 2 amps. And I still have the other 3 resistors, all of them in parallel. I'm going to apply current division so I can find the current flowing through the 8 ohm resistor. And applying Ohm's law across the 8 ohm, I get 3.2 volts. So if we simulate this, the circuit that is on the top, you will see that you have exactly 3.2 volts as an answer. All right. Next one, we have the Thevenin equivalent. So for the Thevenin, what we need to do is we identify the 2 points that we are trying to find that equivalent circuit. And we're going to find the equivalent, the Thevenin resistance and the open circuit voltage. So for the Thevenin resistance, let's short circuit the voltage sources. Let's open circuit the current sources. Find the equivalent resistance, and I get 4 in parallel with 12 plus 1 gives you 4 ohms. Now let's go and find the open voltage circuit. Let's start with identifying here source transformation. So I can pick up the 32 divided by 4, get 8 amps, and that 4 becomes in parallel. And now I can simplify even further. I can put these 2 resistors together and add those 2 currents together, and you get your 10 amps and the 12 in parallel with 4. Apply another source transformation over here, and I get 30 volts and 4 ohms. So my open circuit voltage is 30 volts. My Thevenin equivalent is equal to 30 volts and 4 ohms of Thevenin resistance. So notice that having this circuit over here or this one, it's similar. The exercise is asking for the current for different type of load resistors. So now I put a load resistor here or here, and what is the current that is consuming, and you get this. As you go up or higher in resistance, you get less current. So let's go and simulate this. So on this simulation, I have both circuits there. I have the original circuit with the resistors and the Thevenin equivalent with the load. And if I swap here, notice that I get exactly the same answer, the same current on those 2 circuits. So that's the importance of Thevenin equivalent. All right, so we saw Thevenin. Now let's go over Norton. It's exactly the same thing. We find the Norton, or which is equal to the Thevenin resistance, and we open circuit the current sources, short circuit the voltage sources, and you get 8 plus 4 plus 8, all these in series in parallel with 5, and you get 4 ohms. And we want to find now our short circuit current, and this is by short circuit the terminals and finding which current is passing there. And now notice here that you have a 5 ohm resistor in parallel with a wire. So that means that when current enters this node, the majority of the current is going through the wire. So that means that I can eliminate this 5 and I have just the wire, or you can do the parallel of 5 with a very, very, very small resistance, which gives you that small resistance. And now from here I put the 8s together and I get 16 ohms. And now from here I want to find this one, so I apply KCL over there on that node, and I get 2 equals to the current that flows down plus the current, the short circuit current. Organizing or reorganizing these, I get 2 minus that current, And now let's see how is that current equal to 1 amp. And then because that's 1 amp, you get the short circuit current of 1 amp. So let's see how do I get that I. So looking at the circuit over here, I can rearrange the 16 because everything is in parallel, so I can put it closer to my current source. And now I can apply a source transformation. And notice that I don't lose track of the I. The I is still the same. Even doing this source transformation, the current is still the same, that the one that I want to calculate. From here, I know that I can add the 32 with the 12, and sorry, I can subtract the 12 to the 32 and put in series this resistor, and I get 1 amp. Substituting there, then you calculate your short circuit current. So your Norton equivalent is this one. So let's run the circuit. Let's see the circuit running, and this is what you have: a load of 4 ohms, which is the load that we have. I think I picked up yeah, they didn't have a load, so I pick a random load and I put a 4 ohm resistance, so we can see that we have exactly the same same current here on the original and Norton, and I pick up 4 so you can match the Thevenin resistance that you have. Perfect. So notice that this circuit is way simpler than that one. All right, cool. So now let's go over our last one, the maximum power. So I want to find the RL that gives you the maximum power transfer in the circuit. So the most current and the maximum value for the relationship between current and voltage. For maximum power transfer, we know that the load resistance needs to be equal to the equivalent resistance seen by the circuit. So if I go here, short circuit the voltage sources, open circuit the current sources, find the R equivalent, we get 6 in parallel with 12, in series with 3, in series with 2, 9 ohms, and 9 ohms is the maximum resistance. Now this is the cool one, because we kind of wonder like how, if this is true or not. So I have the circuit here and I have the 9 ohms, and I have here, I'm plotting power. So the watts, how much watts or what is the power of this resistor over here. Notice that I have 11 volts and the current, and now notice that if I put a value that is lower or higher than 9, the value here when I'm plotting should never be higher than 13.4, should always be lower. So let me go and put a value of, let's say, 5 ohms. Notice that the power goes lower. Or let's put 1 ohms, and you see the power going down. All right, let's go back to the 9 ohms. And now let's see, what if I have, let's say, 20 ohms? Notice that the power goes down. What if I have 20k ohms? And the power goes down. And that's the beauty of it. It's like, it's counterintuitive. You think like, oh, maybe it's not like that value, but it shows you that if you match the impedance, you're going to take the most out of your circuit. This could be, for example, the headphones of a system, of a sound system, and you want to listen the songs as loud as possible. So you connect either the headphones or the speakers that they match the impedance, the output impedance of your amplifier. I found it like super cool. All right, cool. If you have any questions, let me know. Hopefully this helps.